On a clear night, if you know where to look, Venus is the brightest thing in the sky besides the moon. It sits there, steady and brilliant, outshining every star. No flickering, no dimness, just a clean, white light that looks almost deliberate. From down here on the surface of Earth, it's beautiful, serene even, almost inviting. But that light is lying to you. What you're actually looking at, from roughly 26 million miles away at its closest approach, is the most hostile environment we've ever found in the solar system. Not hostile in the way Mars is cold and dry. Not hostile in the way deep space is empty and dark. Hostile in a way that combines every possible threat to life and engineering simultaneously. All at once. All the time. The surface of Venus will crush you, bake you, suffocate you, and dissolve you. And it would do all four before you had time to register what was happening. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. Most people don't realize how extreme Venus actually is. We talk about Mars constantly. We send rovers there. We make plans to go there. But Venus, the planet right next door, the planet that looks so calm from Earth's surface, is something else entirely. Here's what makes it strange. Venus and Earth are, by almost every physical measurement, nearly the same planet. Venus has about 95% of Earth's diameter. Its mass is about 81% of Earth's. Its density is close. Its internal composition, iron core, rocky mantle, silicate crust, is believed to be broadly similar. Both planets formed from the same material in the same region of the early solar system, roughly 4.5 billion years ago. For a long time before spacecraft reached it, astronomers genuinely thought Venus might be something like Earth. Warm, maybe. Tropical, perhaps. The clouds that permanently cover it left everything to the imagination, and the imagination filled in lush possibilities. Then we actually sent probes there, and what those probes found rewrote everything. The average surface temperature on Venus is 465 degrees Celsius. That's 869 degrees Fahrenheit. Lead melts at 327 degrees Celsius. Venus's surface is hot enough to melt lead and then keep going. To put that in perspective, a standard kitchen oven tops out around 260 degrees Celsius. Venus is nearly twice that. And unlike Mercury, which swings between extreme heat and extreme cold depending on which side faces the sun, Venus maintains that temperature everywhere, all the time. Day side, night side, poles, equator. The same relentless heat, planet-wide, without variation. The atmospheric pressure at the surface is 92 bars. Earth's sea level atmospheric pressure is 1 bar. What that means concretely is that standing on the surface of Venus, you would feel the equivalent of being nearly a kilometer underwater on Earth. Deep-sea submarines built specifically for those depths are titanium-walled engineering marvels. Even they operate at the limits of what's possible. The Venusian surface would destroy conventional spacecraft in minutes. And then there's the atmosphere itself. It's 96.5% carbon dioxide. There is essentially no breathable oxygen. If the pressure and the heat somehow didn't kill you, you'd suffocate. But we're not done. The clouds that make Venus so beautiful from Earth are not water vapor. They're sulfuric acid, dense, opaque layers of it, wrapping the entire planet from about 45 to 70 kilometers above the surface. Sulfuric acid at concentrations ranging from 75% to nearly 100%. Think about that for a moment. Every layer of this planet's environment is independently fatal. The pressure alone would kill you. The heat alone would kill you. The atmosphere alone would kill you. The acid clouds alone would kill you. Venus has stacked every possible threat on top of each other, and it's been doing it for billions of years. What caused this? That's the question at the heart of what we're going to explore tonight. Because Venus didn't start this way, there's serious scientific evidence, climate modeling, spacecraft data, isotope ratios in the atmosphere, suggesting that Venus may have had liquid water oceans for up to 2 billion years of its early history. 2 billion years of conditions that, at least in some ways, weren't entirely unlike early Earth. And then something went wrong. A feedback loop began. The oceans evaporated, water vapor built up, temperatures climbed, the oceans evaporated further, the loop accelerated. Eventually, the water was gone entirely, hydrogen escaped to space, carbon dioxide built up with nothing to remove it, and the planet locked itself into the state it's been in ever since. That process has a name. It's called a runaway greenhouse effect, and Venus is the clearest example of it anywhere in our solar system. Why does that matter? Because the greenhouse effect isn't something that only happens on distant planets. Understanding how Venus crossed that threshold, what the tipping point looked like, what made it irreversible, is one of the most important questions in planetary science. It sharpens our understanding of what makes a planet habitable. It sharpens our models of how atmospheres behave. It gives us a real physical example of what a planet looks like on the other side of that line. Venus is 26 million miles away at its closest. It's been there the whole time, visible to anyone who steps outside on a clear night and looks west after sunset. And before this night concludes, you will grasp exactly what went wrong, why it matters, and why some scientists think the story of Venus isn't really finished yet. Venus and Earth are, by almost every physical measurement, nearly the same planet. The diameter of Venus is about 95% of Earth's diameter. Their masses are within 20% of each other. Their densities are almost identical. The internal compositions, iron cores, rocky mantles, silicate crusts, are believed to be strikingly similar. These are not vague resemblances. These are precise, measurable similarities that hold up across multiple independent methods of planetary analysis. When astronomers look at the two planets side by side on paper, the numbers line up in a way that is genuinely striking. They formed from the same class of rocky material. They assembled in the same region of the early solar system. For a very long time in the history of planetary science, Venus was considered Earth's natural sibling, not a distant cousin, a sibling. Think about what that means for a moment. Two planets, built from the same ingredients, sitting in the same neighborhood, spinning through the same solar system. Venus orbits the Sun at about 108 million kilometers out. Earth orbits at about 150 million kilometers. In the context of a solar system that stretches billions of kilometers from the Sun to its outer edge, that's practically the same address. They formed around the same time, roughly 4.5 billion years ago, from the same swirling disk of gas and dust that gave birth to everything else in the solar system. If you had watched from a distance in those first few 100 million years, you might not have been able to tell them apart. For a long time, astronomers couldn't tell them apart in any meaningful way. Before spacecraft, before probes, before radar mapping and atmospheric measurements, all anyone could observe from Earth was a bright, featureless disk wrapped in thick, impenetrable cloud cover. And here's the thing. A planet with a thick atmosphere at roughly that distance from the Sun, with a size that close to Earth's, suggested something. It suggested warmth. It suggested pressure. It suggested conditions that could possibly support something like life. Venus sits just inside the inner edge of what astronomers call the habitable zone, the range of orbital distances where liquid water can exist on a planet's surface. Just inside it, not by much. So for most of human history and well into the 20th century, the assumption about Venus was optimistic. If you couldn't see through the clouds and the numbers looked right, the imagination filled in the rest. and the imagination went somewhere lush. Science fiction writers pictured Venus as a kind of jungle world, warm, wet, dense with vegetation, teeming with life under those permanent clouds. It wasn't a fringe idea, it was a reasonable extrapolation from the data people actually had. Carl Sagan himself, early in his career, explored the possibility of a greenhouse Venus before the spacecraft data came in. The clouds hid everything, and in the absence of real data, hope tends to creep in. Then the data came in. The first Soviet probes began reaching Venus in the 1960s. What they sent back was not what anyone had imagined. The atmosphere wasn't tropical, it was crushing. The temperature wasn't warm, it was catastrophic. Venera 4 in 1967 sent back measurements as it descended through the Venusian atmosphere before being destroyed by the pressure. The numbers it returned were so extreme that scientists initially questioned the instruments. The atmosphere was 96% carbon dioxide. The pressure was tens of times greater than anything on Earth's surface. The temperature was hundreds of degrees. The jungle Venus died in an instant. What replaced it was something that didn't have a good name yet. What makes the evil twin comparison so accurate isn't that Venus is completely alien. That's what's so unsettling about it. It's not some strange object assembled from exotic materials we've never seen. Everything that exists on Earth in some form exists on Venus in some form. The iron core is there. Rocky crust. Check. Nitrogen in the atmosphere. Venus's atmosphere is about 3.5% nitrogen, the same gas that makes up 78% of the air you're breathing right now. Volcanic activity. There. Carbon. Sulfur. All the basic planetary ingredients that make Earth what it is are present on Venus. They're just arranged into something horrifying. That's the key word. Transformed. Venus didn't start with different materials. It started with the same materials and then did something catastrophic with them. The nitrogen that floats harmlessly in Earth's air sits on Venus, mixed in with a suffocating weight of carbon dioxide. The iron that forms Earth's protective dynamo-driven core sits in Venus's interior too, but generates no meaningful magnetic field. The volcanic processes that helped shape Earth's surface are present on Venus in overwhelming abundance. Everything Earth has, Venus has a version of, and in almost every case, Venus's version is the thing that kills you. Most people don't realize how specific this is. We're not talking about a planet that's simply hotter or simply more pressurized. We're talking about a planet where every single system that operates reasonably on Earth has been pushed past some critical threshold into something catastrophic. The atmosphere that insulates is now an atmosphere that crushes. The gases that should cycle through air and water are now locked into a permanent suffocating blanket. The clouds that bring rain on Earth bring sulfuric acid on Venus. Acid that falls for kilometers and evaporates before it ever hits the ground. Every parallel leads somewhere awful, and yet the numbers don't lie. Venus's surface gravity is 90% of Earth's. If you could stand on Venus, which you cannot for reasons we're going to get into, you would feel nearly the same gravitational pull as you do right now. You would weigh almost exactly what you weigh on Earth. The planet beneath your feet would be roughly the same size, made of roughly the same stuff, sitting in a solar system you would recognize. The sun would be visible in theory as a dim glow through the cloud cover. It would still be the same sun, and all of that familiarity would be surrounded by conditions that would kill you in seconds. This is what planetary scientists mean when they call Venus a cautionary tale. Not because it's a warning about some specific human behavior, but because it demonstrates that similarity is not the same as safety. Two planets can share almost every fundamental measurement and diverge so completely that one becomes the cradle of all known life and the other becomes one of the most hostile surfaces in the solar system. The difference doesn't have to be enormous to produce catastrophic outcomes. It might be a slightly different orbital distance, a slightly different rate of volcanic outgassing, a slightly different tipping point in the early atmosphere. Small differences, compounded over billions of years, can produce worlds that look nothing alike. The question that drives Venus research, the question that has motivated mission after mission and model after model, is exactly that. What was the difference? Where did the path diverge? Was it always inevitable that Venus would end up this way, given its position? Or did Venus have a window of stability that it eventually lost? Some scientists believe Venus may have been genuinely habitable for its first 2 billion years. Similar oceans, similar temperatures, similar atmospheric conditions. If that's true, then the catastrophe wasn't built into Venus from the beginning. Something changed. Something tipped it over. And identifying that tipping point matters enormously, not just for understanding Venus, but for understanding what makes any planet stable. They had the same raw materials, the same starting conditions, and they ended up in completely different places. And figuring out why is one of the most important questions in planetary science. The surface of Venus sits at an average temperature of 465 degrees Celsius. That's 869 degrees Fahrenheit. Those numbers might not mean much on their own, so let's put them in context. Lead melts at 327 degrees Celsius. The surface of Venus is hot enough to melt lead and still have more than 130 degrees to spare. Zinc melts at 420 degrees. Tin melts at 232 degrees. These are metals we think of as sturdy, industrial, built to handle heat. On Venus, they wouldn't survive. They'd pool on the ground like water. Most people assume Mercury must be the hottest planet. It makes sense. Mercury is the closest planet to the Sun. It gets hit with about 4 times more direct solar radiation than Venus does. On the side facing the Sun, Mercury's surface can reach around 430 degrees Celsius. That's genuinely extreme. But Venus beats it. Venus beats it by nearly 40 degrees. And Mercury's dark side, the side turned away from the Sun, drops to around negative 180 degrees Celsius. The temperature swings wildly depending on where you are and what time it is. Venus doesn't do that. Venus doesn't swing at all. The entire surface of Venus sits at roughly the same temperature. Day side, night side, equator, poles. It doesn't matter. The thick atmosphere traps heat so efficiently that it distributes it almost perfectly across the whole planet. The night side of Venus, which receives 0 direct sunlight, is still around 460 degrees Celsius. Think about what that means. Venus is farther from the Sun than Mercury. It absorbs less direct solar energy. And yet it's hotter everywhere, all the time, than Mercury ever gets at its hottest point. The greenhouse effect operating on Venus isn't just powerful, it's total. Now think about what it would actually mean to stand on that surface. Not that any human being would survive long enough to form a coherent impression, but walk through it for a moment. The moment you arrived, the pressure would hit you. The atmospheric pressure at Venus's surface is 92 times greater than what we experience on Earth at sea level. That's roughly equivalent to being submerged a full kilometer underwater on Earth, 1 kilometer down. The deepest recreational divers in the world reach perhaps 300 meters under extraordinary conditions with specialized equipment. A kilometer underwater is the domain of titanium-hulled submersibles with walls inches thick, engineered to a precision that takes years to achieve. And even those vehicles are operating right at the edge of what engineering can currently manage. On Venus, that pressure isn't something you descend into carefully in a reinforced hull. It's just the air. Standing on the ground, you'd be crushed before any other threat had a chance to matter. But let's say somehow the pressure wasn't a problem. Then the heat. 465 degrees Celsius surrounds you completely, not in one direction, not from above, from every direction, because the air itself is that temperature. The rocks are that temperature. The ground under your feet is that temperature. You're not being exposed to a heat source, you're inside the heat. The distinction matters. On a hot day on Earth, you can step into shade. You can move away from the sun. On Venus, the heat is the environment. There is no shade. There is no cooler direction to face. The entire world is a furnace at the same setting. Then there's the air itself. 96.5% carbon dioxide, effectively no oxygen. If the pressure and the heat hadn't already ended things, the atmosphere would finish the job almost instantly. You couldn't breathe. There's nothing there to breathe. And the carbon dioxide surrounding you isn't an abstract chemical statistic. It's the very substance that created the furnace in the first place, the gas that locked all that heat in and won't let it out. The atmosphere itself transforms the landscape chemically. At Venus's surface, the extreme temperatures and pressures cause reactions that don't occur anywhere else in the solar system. The carbon dioxide doesn't remain as an inert gas. It participates in reactions with surface minerals, with the rocks themselves. Sulfuric acid clouds high in the atmosphere rain down or evaporate before reaching the ground, but the processes that create them are happening constantly, powered by solar energy and the planet's rotational dynamics. The air moving across the volcanic surface carves weathering patterns, but unlike water erosion on Earth, it leaves behind angular, sharp features. The rocks don't round. They fracture. They splinter. Time on Venus works differently than it does here. The extreme environment accelerates some processes while halting others entirely. What does the surface actually look like? The Venera landers gave us our only direct images, and those images are striking in their own way. The landscape is volcanic, almost entirely, overwhelmingly volcanic. Vast plains of hardened lava stretch across most of the planet. Shield volcanoes rise from the surface, enormous structures, some of them larger than anything on Earth. Maxwell Montes, the highest mountain range on Venus, reaches about 11 kilometers above the mean surface elevation. That's taller than Everest above sea level. There are highland regions, lowland plains, and enormous volcanic features that have no real equivalent anywhere else in the solar system. These volcanoes appear geologically young. Many may still be active, though we've never caught definitive proof of eruption in progress. The lava flows are incredibly smooth and fluid, suggesting they flowed far across the surface before cooling, a process enabled by the extreme heat that keeps the rock malleable far longer than on Earth. What you won't find is any sign of water, no riverbeds carved into rock, no shorelines worn smooth by ancient waves, no sedimentary layers built up over millions of years of ocean floor deposition. On Earth, water shapes everything. It carves canyons, it rounds rocks, it builds beaches. The absence of those features on Venus tells a story about what the surface has been through and what it hasn't. It hasn't had water for a very long time. Whatever rivers and oceans may have existed billions of years ago left almost nothing behind. The volcanic activity essentially erased and remade the surface. What we're looking at when we study Venus is a landscape defined entirely by fire, not water. The light on the Venusian surface is dim and orange. The dense cloud layers block most of the sunlight before it reaches the ground, filtering it into something closer to a perpetual overcast twilight. The Venera images show rocks bathed in that orange glow, angular and flat, scattered across the surface. No soft edges, no sand, no rounding from erosion, just dark volcanic rock under a sky the color of a rusted ceiling. It would be deeply alien, but not in a dramatic cinematic way. Strange and dead and silent, except for the wind moving slowly through air as thick as shallow water. We sometimes talk about hostile environments on Earth, the Sahara, the poles, the deep ocean trenches. But none of those places combine all their threats the way Venus does. The deep ocean is crushing but cold. The Sahara is hot but breathable. Antarctica is brutal but survivable with the right gear. Venus layers every single threat on top of every other threat simultaneously, and then removes every resource you might use to fight back. There's no water, no oxygen, no moderate temperature anywhere on the planet, no sheltered valley, no cave, no altitude that offers relief. The mountains are just as hot as the plains. The poles are just as hot as the equator. The night is just as hot as the day. The best probe humanity ever landed on Venus survived for 127 minutes. That was Venera 13, built by the Soviets with the specific goal of enduring as long as possible. It was reinforced, insulated, and designed by some of the best engineers of the era, working with full knowledge of what the surface conditions would be. And it lasted 127 minutes. Not because of any design flaw, not because of bad luck, because Venus's surface is operating at a level of sustained hostility that simply dismantles anything we build, given enough time. 2 hours and 7 minutes was the best we ever achieved. The numbers for Venus's surface don't build towards something comprehensible. They just keep excluding things. Too hot for metals, too pressurized for conventional structures, too oxygen-free for life as we know it, too uniformly extreme for any natural shelter to exist. Our usual frameworks for thinking about dangerous environments break down completely when you apply them to Venus. It's not just hot, it's uniformly, relentlessly, inescapably hot. A world baked to the same temperature everywhere, all the time, with no variation and no relief. The atmospheric pressure at the surface of Venus is 92 bars. That number doesn't mean much on its own, so let's put it in terms that actually land. Earth's atmospheric pressure at sea level is 1 bar. That's what you feel every day without noticing it, the weight of the air above you pressing down on your body. Venus has 92 times that. Every square inch of the Venusian surface has the full weight of that atmosphere pushing down on it. We're talking about roughly 1,350 pounds per square inch. Imagine a small car, something around 1,300 or 1,400 pounds. Now imagine that car balanced on an area the size of your thumbnail. That's what the atmosphere of Venus does to every surface it touches, constantly, without stopping. Most people don't realize how little pressure variation humans can actually tolerate. We're built for a very narrow range. Recreational divers typically go to around 30 or 40 meters beneath the ocean surface. That's about 3 to 4 atmospheres of pressure, already enough to require careful training and specialized equipment to handle safely. Go deeper, and the risks multiply quickly. Specialized divers with the right gear can push to around 100 meters in controlled conditions. That's about 10 atmospheres. Beyond that, the human body starts to fail in ways that can't be compensated for with training alone. The pressure becomes a physical force that the body simply can't manage. Now consider what 1 kilometer underwater actually means. At that depth, you're looking at roughly 100 atmospheres of pressure. That's close to what you'd find on the surface of Venus. And humanity has sent vehicles to those depths, remotely operated submersibles, crewed research vessels, titanium-hulled spheres engineered with walls several inches thick to withstand the crushing weight of the ocean above them. These aren't simple machines. They represent some of the most demanding engineering challenges we've ever attempted. Even with all that precision, deep-sea exploration remains extraordinarily difficult. The margin for error is almost non-existent. A flaw in the hull, a seal that isn't perfect. The ocean finds it immediately. Venus offers those same conditions. But instead of a column of water pressing down from above, it's a column of dense carbon dioxide-heavy atmosphere, stretching dozens of kilometers into the sky. The pressure is not a feature of Venus's surface. It's everywhere, at once, in all directions. It doesn't press from above. It presses from every angle simultaneously, crushing inward with no relief. A human being standing on the surface of Venus, setting aside the 465-degree heat and the toxic air, would be destroyed by the pressure alone in an instant. There's no suit, no material we currently have that would protect a person at that depth of atmospheric pressure. It's not a survivable environment by any stretch of current engineering. The early Soviet scientists who designed the first Venera probes didn't fully appreciate that. It's easy to say that in hindsight, but the truth is that nobody did. Venus, when viewed through Earth's telescopes, looked like a planet wrapped in clouds. The assumption was that those clouds concealed something moderately hostile, perhaps hot, perhaps stormy, but probably manageable with a well-built probe. The first probes were built to handle what engineers thought would be the conditions. They were wrong. Venera 3 reached Venus in 1966. It became the first human-made object to contact the surface of another planet, but it was crushed before it could transmit a single piece of data from below the clouds. It never had a chance. The atmosphere was far denser, far heavier, far more destructive than anyone had calculated. The probe simply ceased to exist as a functioning machine. Venera 4 followed in 1967. It was built stronger. It sent back data as it descended through the atmosphere, but it too was crushed before it reached the surface. The Soviets were still underestimating the depth and the pressure of what they were dealing with. Each mission taught them something about just how extreme the conditions really were. They kept building stronger, more resilient probes, and Venus kept destroying them, each time a little deeper into the descent, each time revealing a little more about how hostile the environment actually was. It wasn't carelessness. It was a genuine failure of prior understanding, corrected mission by mission at enormous cost. What makes the pressure of Venus's atmosphere so hard to grasp is that it doesn't look like pressure. It looks like air. From above the clouds, Venus looks like any other planet wrapped in weather. There's no visual cue that you're looking at an atmosphere that would crush a submarine hull. The pressure is invisible. It only announces itself when something tries to exist inside it. There's another aspect of this dense atmosphere that most people don't think about. Wind speed near the surface of Venus is actually quite slow, around 2 to 3 meters per second. By Earth standards, that's barely a breeze. You'd feel it, but it wouldn't knock you over. On Earth, a 2 meter per second wind carries very little force, but Venus's lower atmosphere isn't like Earth's air. It's so thick, so dense, so compressed by the enormous pressure above it, that its density approaches something closer to a liquid than a gas. Think about what it feels like to move your hand through water versus through air. The water pushes back with real force even at low speeds. A 2 meter per second current in a river can move you if you're not braced for it. The lower atmosphere of Venus behaves similarly. A gentle wind at the surface carries the momentum of something far heavier than air. If you placed any structure on the Venusian surface, that slow-moving atmospheric mass would push against it with substantial force, even without any kind of storm or gust. This density also has consequences for heat. A thicker atmosphere doesn't just add pressure, it traps heat more effectively. The atmospheric pressure on Venus is part of what makes its greenhouse effect so catastrophic. More atmosphere means more molecules available to absorb and re-radiate heat, which means less heat escapes to space. The two properties reinforce each other. The pressure isn't just crushing, it's also one of the mechanisms keeping all that heat locked inside. Venus isn't just hot and heavy. It's hot because it's heavy. The mass of the atmosphere is doing double duty, pressing down on the surface and sealing the heat in at the same time. The density of the lower atmosphere also matters for any future engineering effort to operate on Venus's surface. Any lander, any rover, any stationary probe would have to be built not just to withstand the temperature, but to handle a constant crushing force applied equally from all directions, plus the slow but forceful push of a low-speed wind dense enough to behave like moving water. The engineering requirements are extraordinary. Every component has to be rated for pressure far beyond anything used in ordinary aerospace engineering. Every seal, every joint, every structural element has to hold under conditions that have destroyed everything we've ever sent there. Those first Soviet probes that tried to land on Venus were crushed by an atmosphere they hadn't fully anticipated, and that failure taught us just how extraordinary the pressure really is. The greenhouse effect that destroyed Venus didn't happen overnight. It took hundreds of millions of years. It followed a chain of events that, once started, couldn't be stopped. And understanding it requires starting somewhere that might seem surprising, with the idea that the greenhouse effect itself is not the problem. The greenhouse effect is why we're alive. Earth has a greenhouse effect. It's always had one. Carbon dioxide, water vapor, methane, and other gases in our atmosphere trap heat that would otherwise radiate out into space. Without that, Earth's average surface temperature would be somewhere around -18 degrees Celsius. That's below the freezing point of water. The oceans would be frozen. Life as we know it almost certainly wouldn't exist. The greenhouse effect isn't a flaw in our planet's climate system. It's the reason our planet has a climate system worth talking about. What happened on Venus was something categorically different. A runaway greenhouse effect isn't just a stronger version of what Earth has. It's a process that crosses a threshold, triggers a feedback loop, and then cannot reverse. The warming causes more warming, which causes more warming, until the system reaches a new state that is nothing like where it started. That's the key word, runaway. Once it begins, there's no mechanism to slow it down. It consumes itself until it's finished. Scientists believe the process on Venus started with the sun. The early sun was dimmer than it is today, roughly 30% less luminous when the solar system was young. That lower output meant Venus, despite its closer position, received less energy than it does now. Over billions of years, the sun gradually brightened. This is a normal part of stellar evolution. All stars like our sun get slowly, steadily brighter as they age. For Earth, that gradual brightening has been offset by geological and biological processes that have kept the climate relatively stable over time. For Venus, something went wrong. As the sun brightened, Venus absorbed more energy. Temperatures at the surface rose slightly. That slight rise caused more water to evaporate from Venus's early oceans. Here's where the feedback loop begins. Water vapor is itself a greenhouse gas. More water vapor in the atmosphere means more heat is trapped. More trapped heat means higher temperatures. Higher temperatures mean more evaporation. More evaporation means more water vapor. The loop tightens. It doesn't stop. Think about what that means. The oceans weren't instantly boiled away. It was gradual, but the direction was locked. Every step in the process pushed Venus toward higher temperatures, and higher temperatures fed back into the process that was causing them. There was no counterbalancing force strong enough to interrupt it. On Earth, when temperatures rise, increased rainfall can pull carbon dioxide out of the atmosphere, slightly cooling the planet. That kind of chemical counterbalancing never had a chance to stabilize Venus once the feedback loop reached a certain intensity. The sheer accumulation of water vapor in the atmosphere created a thickening blanket that became increasingly effective at trapping heat. Each additional molecule of water vapor added to the atmospheric envelope intensified the effect that was driving more evaporation. The system spiraled upward in temperature across thousands of years, then tens of thousands of years. There was no pause, no plateau, no moment where equilibrium reasserted itself. The feedback mechanism was perfectly efficient at doing only one thing: pushing the system toward greater and greater heat. Eventually, the oceans evaporated completely, not in a dramatic single event. Over geological time, the surface water disappeared. What had once been an ocean world became dry, but the water didn't just vanish, it entered the atmosphere as vapor. And then something else happened. In Venus's upper atmosphere, ultraviolet radiation from the sun broke apart those water molecules. A water molecule is 2 hydrogen atoms and 1 oxygen atom. When UV radiation hits it with enough energy, it splits. The hydrogen, the lightest element in the universe, escaped into space. Gone. The oxygen remained behind and reacted with rocks and surface minerals. Over time, the water that had once covered the surface of Venus was chemically dismantled. The hydrogen drifted away into the void. The oxygen was absorbed into the ground. This photodissociation process operated silently and inexorably, molecule by molecule, gradually erasing Venus's water reserves from the top of its atmosphere downward. The process accelerated as temperatures climbed, because higher atmospheric temperatures meant water vapor extended into higher altitudes where UV radiation was more intense and more capable of breaking molecular bonds. What had once been oceans became atmospheric water vapor, and what had been atmospheric water vapor became separated hydrogen and oxygen, and the hydrogen simply escaped. There was no mechanism to recapture it. This is a one-way process. There's no mechanism to reverse it. Once the hydrogen is gone, there's no putting the water back together. Venus lost its water permanently, and with it, something critical: the carbon cycle. On Earth, the carbon cycle is what keeps carbon dioxide from accumulating in the atmosphere indefinitely. When it rains, the water dissolves small amounts of carbon dioxide from the air, forming a weak carbonic acid. That slightly acidic rain falls on rocks and reacts with minerals, breaking them down and forming carbonates. Those carbonates wash into the ocean. They get incorporated into the shells of marine organisms. Eventually, through plate tectonics, they get drawn into the crust and recycled into the mantle. Carbon dioxide gets sequestered. It gets pulled out of circulation. This is why Earth hasn't cooked itself. The planet has a mechanism for removing carbon dioxide from the atmosphere as fast as it's added. Venus lost that mechanism when it lost its water. No water means no rain. No rain means no weathering of rocks in the carbonic acid sense. No weathering means no carbonate formation. No carbonates means no way to pull carbon dioxide out of the air. The carbon cycle, which depends entirely on liquid water as its working fluid, simply stopped. Volcanic outgassing continued its steady release of carbon dioxide from the planet's interior, but with the carbon cycle broken, there was no corresponding removal process to balance that outgassing. The atmospheric composition began to shift dramatically. Carbon dioxide, which had always been present, began to accumulate at increasing concentrations because the geological sink that normally captured it no longer functioned. And Venus has volcanoes, a lot of them. Volcanism releases carbon dioxide from the interior of a planet into its atmosphere. On Earth, that outgassing is continuously offset by the carbon cycle pulling carbon dioxide back out. On Venus, after the water was gone, the outgassing continued with nothing to balance it. Carbon dioxide from the planet's interior accumulated in the atmosphere. More carbon dioxide meant a stronger greenhouse effect. A stronger greenhouse effect meant higher temperatures. Higher temperatures meant the planet's remaining water, if any existed in subsurface reservoirs, had even less chance of surviving. The process compounded itself. The atmosphere of Venus today is 96% carbon dioxide. That's not a slight variation from Earth's atmospheric composition. Earth's atmosphere is about 0.04% carbon dioxide. Venus has more than 2,000 times as much carbon dioxide in its atmosphere as Earth does proportionally. That's the endpoint of the runaway process. That's what accumulates when a carbon cycle breaks down and volcanic outgassing runs unchecked for billions of years. The surface temperature that results from all this is 465 degrees Celsius, a greenhouse effect strong enough to push the temperature higher than Mercury, a planet that sits far closer to the Sun and gets hit with far more direct solar radiation. Mercury has no atmosphere to speak of. Venus has too much atmosphere, one extreme and the other, both deadly. But Venus is actually hotter, which tells you something about how extraordinarily effective that thick carbon dioxide blanket is at trapping energy. What makes this so important is that it's not a model or a prediction. It's not something scientists are warning might happen on some other world at some theoretical point in the future. It already happened. The evidence is observable. The composition of Venus's atmosphere is measurable. The temperatures are measurable. The absence of water is measurable. We can look at the ratio of deuterium to regular hydrogen in Venus's atmosphere and see the fingerprint of enormous water loss over geological time because deuterium is heavier than hydrogen and escapes more slowly, concentrating in the atmosphere as the lighter hydrogen flees to space. Venus carries the record of what happened to it written into its chemistry. We can read that record, and what it tells us is that a world very similar to Earth triggered a feedback loop it couldn't survive. It started with a small increase in solar energy, not a dramatic spike, just the slow, ordinary brightening of a middle-aged star. That was enough. A little more heat led to a little more evaporation, which led to a little more warming, which led to more evaporation. The loop didn't require a catastrophic outside event. It didn't require an asteroid or a nearby supernova. It required only conditions that pushed the system slightly past a threshold, and then the system destroyed itself. And when that feedback loop completed, when the oceans were gone and the carbon dioxide had nowhere to go, Venus sealed itself into the state it's been in ever since. For the first 2 billion years of its existence, Venus may have looked nothing like what it is today. That's a hard thing to absorb. We've spent the last several minutes talking about a planet that melts lead, crushes spacecraft, bakes everything on its surface to the same relentless temperature around the clock. And now the claim is that this same world may have once had oceans, shallow seas, rocky coastlines, liquid water sitting on the surface under an open sky. The evidence for this is not speculation. It comes from spacecraft data, from climate modeling, from a specific chemical fingerprint still sitting in Venus's atmosphere right now, a fingerprint that points directly to water that used to exist and doesn't anymore. To understand how scientists arrived at this, you have to go back to the early solar system. When Venus and Earth formed, roughly 4.5 billion years ago, the Sun was not the same star it is today. The young Sun was about 30% dimmer than it currently is. That matters enormously. A dimmer Sun means less energy reaching the inner planets. Venus sits closer to the Sun than Earth does, but with a dimmer star and a possibly different early atmospheric composition. The amount of solar energy reaching Venus's surface was low enough that the planet could have maintained temperatures compatible with liquid water. The models suggest this window lasted a long time, not millions of years, billions. NASA researchers at the Goddard Institute for Space Studies ran climate simulations specifically designed to model early Venus. These are the same general computational tools used to model climate change on Earth, adapted to account for Venus's slightly different size, its rotation rate, what its atmosphere may have contained before the runaway greenhouse effect took hold. What the models returned was striking. Under those early conditions, Venus could have sustained a stable climate with surface temperatures somewhere between 20 and 50 degrees Celsius. Warm, but not lethal. Warm enough for liquid water to exist on the surface for an extended stretch of geological time. Some models put that window as long as 2 billion years. 2 billion years of habitable conditions. That's not a brief window. That's nearly half the current age of the solar system. But climate models are models. They're powerful tools, but they rely on assumptions about initial conditions that we can't perfectly reconstruct. You might reasonably ask whether there's any physical evidence, any direct observational data, pointing toward ancient water on Venus. And that's where the Pioneer Venus mission comes in. In the early 1980s, NASA's Pioneer Venus spacecraft studied the composition of Venus's upper atmosphere in detail. Among the measurements it took was the ratio of deuterium to ordinary hydrogen. Deuterium is sometimes called heavy hydrogen. It's a version of hydrogen with an extra neutron. That makes it heavier than standard hydrogen. Water molecules on Earth contain ordinary hydrogen, but some water molecules contain deuterium instead, forming what's called heavy water. On Earth, the ratio of deuterium to regular hydrogen in our water is very low. This was because Earth still has enormous quantities of water, and the proportions haven't changed dramatically. On Venus, the Pioneer spacecraft measured a deuterium to hydrogen ratio roughly 150 times higher than on Earth. Think about what that means. When water is lost from a planet's atmosphere, it happens because water molecules drift into the upper atmosphere, get split apart by ultraviolet radiation from the sun. The resulting hydrogen atoms escape to space. Standard hydrogen is lighter, it escapes faster. Deuterium is heavier, so it escapes more slowly. Over geological time, if a planet loses most of its water this way, deuterium gets left behind while the regular hydrogen bleeds off into space. The ratio shifts. The more water you lose, the more the ratio climbs. A ratio 150 times higher than Earth's tells you that Venus once had a tremendous amount of water and lost nearly all of it through exactly this process. This is one of the most important measurements ever made in planetary science. It's not a computer model, it's a direct chemical measurement from an actual spacecraft. And it says that Venus had water, a lot of it, and that the water is gone now. Exactly how much water Venus once had is harder to pin down. Some estimates suggest it may have had a global ocean averaging perhaps a few hundred meters deep. Not as deep as Earth's oceans, which average around 3,700 meters, but enough to cover much of the surface, enough to drive weather patterns, enough to support a functioning water cycle with evaporation, clouds, rainfall, liquid water rainfall, not the sulfuric acid virga that falls and evaporates in the Venusian atmosphere today. A shallow, warm, global sea. Rocky continents rising above the waterline, river channels cutting through volcanic rock, coastlines. What did that world actually look like? There's no way to know with certainty. The surface of Venus has been almost entirely reshaped by volcanic activity. Nothing resembling ancient ocean floors or riverbeds has been identified in the radar imaging we have. The evidence is chemical, not geological, but we can make reasonable inferences. Early Venus likely looked something like early Earth, rocky, tectonically active, volcanically productive, covered in shallow, warm water. The sky would have been different. The composition of the early atmosphere, before the greenhouse effect locked in, was probably closer to what Earth's early atmosphere looked like. Not breathable by human standards, but chemically very different from the carbon dioxide furnace that surrounds Venus today. And this is where things become genuinely unsettling. Life on Earth emerged roughly 3.5 to 4 billion years ago, possibly even earlier. It appeared in the first billion years of the planet's existence. while conditions were still young and the chemistry of the early oceans was playing out. Scientists don't fully understand how life emerged, but the conditions required appear to include liquid water, chemical gradients, and energy sources. Early Venus had all of those. For potentially 2 billion years, if life can emerge from the right conditions, and Earth suggests that it can, that it does so relatively quickly once those conditions exist, then Venus had twice as long as Earth's first billion years to allow that process to happen. Whatever lived on early Venus, if anything did, had enormous stretches of time to develop. We don't know whether life ever appeared there. We have no way to know. The surface has been completely transformed. Any record of ancient biology, if it ever existed, has been erased by billions of years of volcanic resurfacing and heat intense enough to restructure rock. But the question is worth sitting with. We tend to think of Venus as always having been a hellscape. It wasn't. It was a world that started from roughly the same place Earth did, had roughly the same early conditions Earth did, had those conditions for a long time, and then it transformed. Whatever the transition looked like from the inside, and it was almost certainly a gradual process over hundreds of millions of years, the end result was the complete obliteration of every surface condition that could support life as we understand it. There's one more piece of the picture worth mentioning. Venus's slow rotation, it takes 243 Earth days to complete one rotation on its axis, may have actually helped stabilize its early climate in ways that weren't obvious at first. Scientists studying early Venus have suggested that a slowly rotating planet develops a different cloud pattern than a faster spinning one. The models indicate that a slowly rotating early Venus may have developed thick clouds on its day side, the side facing the sun, which would have reflected significant solar energy and helped keep surface temperatures from climbing too high. That cloud behavior may have extended the habitable window, buying Venus additional geological time before the warming trend overcame the stabilizing mechanisms. That window closed. We know how it closed. The previous section covered the mechanics of the runaway greenhouse effect in detail. The feedback loops between water vapor, temperature, and evaporation accelerated. The oceans evaporated. The hydrogen escaped to space. The carbon cycle broke down with no liquid water left to maintain it. Carbon dioxide accumulated. The greenhouse effect intensified beyond any recovery point. And Venus locked into the state it's been in ever since, a surface temperature of 465 degrees Celsius, a crushing atmosphere of mostly carbon dioxide, no liquid water anywhere. The oceans are gone. The hydrogen has escaped to space. The only trace of all that water is a ratio of isotopes in the atmosphere that tells us something enormous used to be there. Every square inch of Venus's sky is covered by clouds. Not the kind of clouds you see from an airplane window. Not the scattered white puffs drifting over an ocean on a summer afternoon. The clouds on Venus are permanent. They're planet-wide. They've been there for billions of years, and they don't move in the way clouds move on Earth. They don't part. They don't thin out. They don't let light through. From space, Venus looks like a smooth, featureless sphere, uniformly bright because the cloud cover is so complete and so dense that you can't see the surface at all. You could orbit Venus for a lifetime and never catch a glimpse of the ground beneath you. The clouds start at around 45 kilometers above the surface and extend upward to about 70 kilometers. That's a band of cloud roughly 25 kilometers thick, wrapped entirely around the planet, blocking almost everything. And what they're made of is not water. The clouds of Venus are composed almost entirely of sulfuric acid, not weak sulfuric acid, not diluted sulfuric acid. Concentrated sulfuric acid droplets ranging from about 75% to 98% concentration. That's roughly the same concentration used in industrial manufacturing on Earth. Battery acid is about 30% to 50%. The clouds on Venus are far stronger than that. A droplet of sulfuric acid at that concentration will dissolve most metals, most organic materials, most things we might think of as durable. The clouds aren't just obscuring Venus's surface from view, they're chemically hostile in a way that's difficult to even frame in familiar terms. Most spacecraft materials wouldn't last long inside them. How did Venus end up with a sky full of sulfuric acid? The answer starts with the planet's volcanoes. Venus is extraordinarily volcanic, more volcanoes than any other planet we know of, and those volcanoes constantly outgas sulfur dioxide into the atmosphere. Sulfur dioxide rises. It gets carried up through the lower atmosphere and into the upper cloud layers, where solar ultraviolet radiation takes over. The UV light drives photochemical reactions between the sulfur dioxide, the carbon dioxide, and the small traces of water vapor still present in the upper atmosphere. The result of those reactions is sulfuric acid. It forms as tiny droplets. Those droplets aggregate into clouds. The cycle feeds itself continuously as long as Venus's volcanoes keep producing sulfur dioxide, which they do. On Earth, this doesn't happen. Sulfur dioxide from volcanic eruptions does enter Earth's atmosphere, but it's removed within days. Rain dissolves it. Moisture neutralizes it. The hydrological cycle cleans it out constantly and efficiently. Earth essentially scrubs its atmosphere of sulfur dioxide before it can accumulate into anything like what Venus has. Venus lost that cleaning mechanism when it lost its water. Without rain, without moisture, without any mechanism to wash the sulfur dioxide out of the atmosphere, the gas persists. It accumulates. It keeps reacting, keeps producing acid, keeps replenishing clouds that have nowhere to go and nothing to dissolve them. Here's something that takes a moment to fully absorb. Those clouds reflect about 70 to 80% of the sunlight that hits Venus. Think about what that means. Venus is closer to the sun than Earth. It receives more incoming solar radiation. But because its clouds reflect so much of that radiation straight back into space, Venus actually absorbs less solar energy than Earth does. Mercury has almost no atmosphere and no clouds. The sun beats down on Mercury's surface directly. During the day, Mercury's surface temperature reaches around 430 degrees Celsius. Venus, farther away and reflecting most of the sunlight hitting it, should in theory be cooler than Mercury's day side. It isn't. Venus's surface averages 465 degrees Celsius all the time. The heat that does make it through the clouds gets trapped so effectively by the dense carbon dioxide atmosphere below that the surface temperature climbs far beyond what Mercury ever reaches, even on its sun-facing side. Venus beats Mercury on temperature despite catching far less sunlight. That's the greenhouse effect doing extraordinary work, so the light barely gets in. But what about when the sulfuric acid actually falls? Because it does fall. The clouds produce acid rain in a very real sense. Droplets grow heavy enough and begin to descend toward the surface. They fall through tens of kilometers of atmosphere, getting lower and lower. And then something happens. The temperature rises sharply as they descend. By the time the droplets have fallen far enough, the heat is too extreme for them to survive as liquid. They evaporate. The acid that was falling simply disappears, converts back into vapor, and gets carried back up by atmospheric circulation to form clouds again. This phenomenon has a name. It's called virga. Virga occurs on Earth too, in dry desert climates when rain evaporates before it reaches the ground. On Earth, it's unusual. On Venus, it's the only kind of rain that exists. The acid forms, falls for kilometers, evaporates, and recycles back into the clouds. It has been doing this continuously. The surface of Venus has probably not felt a drop of liquid in billions of years. The clouds don't look the same to every instrument, though. In visible light, Venus is a smooth, cream-colored sphere with no surface features visible and almost no detail in the clouds themselves. It looks almost artificial in its uniformity. But in ultraviolet light, something different appears. The cloud tops become banded. Streaks of dark material appear across the upper layers, dark regions that absorb ultraviolet radiation more strongly than the surrounding cloud. These streaks aren't random. They're structured. They persist. They hold together despite wind speeds in the upper atmosphere reaching around 360 kilometers per hour. That's close to the wind speed of the most powerful hurricanes on Earth. Yet these features maintain their form and keep absorbing UV light. What they're made of isn't fully established. The most straightforward explanations are chemical. Iron chloride is one candidate. Certain sulfur compounds can form structures that absorb UV radiation strongly. These are probably what the dark streaks are. But a smaller group of scientists has pointed out something worth considering. The UV absorption profile of the dark streaks, the specific wavelengths they absorb and how they re-radiate that energy, resembles what some microorganisms do on Earth. Some bacteria use similar chemical mechanisms to protect themselves from ultraviolet light. The particles detected in Venus's lower cloud layers by Soviet Venera probes were roughly the size of a bacterium. None of this is evidence for life. The scientific consensus leans heavily toward a chemical explanation, but the hypothesis hasn't been definitively ruled out, and for a planet that may have had oceans for 2 billion years, the question feels worth asking. The cloud layers also have a structure to them. They're not a single homogeneous mass. There are distinct layers within the 25-kilometer thick cloud band, each with slightly different compositions and droplet sizes. The upper layers, around 65 to 70 kilometers, contain the most concentrated acid. The middle layers are somewhat denser. The lower edges of the cloud, approaching 45 kilometers altitude, begin to transition into a haze layer that stretches down toward the bare atmosphere below. Below about 30 kilometers, the atmosphere clears. The acid rain has evaporated by then. What's left is a clear, dim, orange-tinted atmosphere pressing down toward the surface, carrying its enormous pressure and heat without any clouds to see. The surface itself is never touched by the acid, never cooled by rain, never reached by more than a fraction of filtered sunlight. It just sits there, baking, under kilometers of toxic atmosphere with a permanent acid sky far above it. Venus reflects so much light precisely because of these clouds. It's why the planet is so bright from Earth, why it's been mistaken for strange objects in the sky, why ancient civilizations tracked it with such precision. The beauty is the acid. The brilliance is the poison. The cloud cover that makes Venus the brightest planet in our sky is the same cloud cover that makes the surface utterly continuously unreachable. That rain falling for hundreds of kilometers without ever hitting the ground, cycling back up to fall again. It's one of the strangest weather systems we know of anywhere in the solar system. Venus has more volcanoes than any other planet we know of. Over 1,600 major volcanoes have been identified on its surface, and that number almost certainly understates the reality. When scientists include smaller volcanic features, the domes, the calderas, the low shield structures scattered across the plains, the total count runs into the hundreds of thousands. No other planet in our solar system comes close to that density of volcanic activity, at least not in terms of what's preserved on the surface. Think about what that number actually means. Earth has roughly 1,500 volcanoes considered potentially active. Venus has that many major ones alone, and the planet is slightly smaller than Earth. The entire surface of Venus is dominated by volcanic features in a way that Earth's is not. Vast lava plains stretch across most of the planet's lowlands. Shield volcanoes rise from the surface, some of them comparable in scale to the largest volcanoes on Earth. There are structures on Venus called coronae, roughly circular volcanic features surrounded by rings of ridges and troughs that don't really have a direct equivalent anywhere else we know of. The geology of Venus is, in almost every respect, a volcanic story. To understand why, you have to understand what's happening inside the planet. Venus and Earth have similar interior compositions. Both have an iron core, a rocky mantle, and a crust. Both generate heat internally through the radioactive decay of elements like uranium, thorium, and potassium. That process doesn't stop. It's been running since the planets formed, and it's still running now. The heat has to go somewhere. On Earth, it goes through plate tectonics. The crust is broken into massive plates that move, collide, slide beneath one another, and slowly recycle the surface. It's a continuous, gradual process. Heat escapes steadily. The surface gets renewed over hundreds of millions of years. Venus doesn't appear to work that way. There's no clear evidence of active plate tectonics on Venus. The crust seems to be one continuous shell, not divided into moving pieces. So how does all that internal heat escape? That's the question that defines Venusian geology, and the answer, as best as scientists can determine, is that it doesn't escape gradually. It builds up, and then it doesn't escape gradually at all. Scientists call this the heat release paradox. Venus is generating internal heat at roughly the same rate as Earth, but without plate tectonics providing a continuous release mechanism, that heat accumulates beneath the crust. The crust thickens and stiffens. Pressure builds from below, and the leading hypothesis is that Venus periodically reaches a breaking point, a threshold where the accumulated heat can no longer be contained, and the entire crust essentially collapses and overturns in a catastrophic burst of volcanism that resurfaces most of the planet in a geologically brief period. Brief in geological terms, of course. We're talking about something that probably plays out over tens of millions of years. But compared to the slow, continuous recycling on Earth, it's an eruption of geological activity on a planetary scale. The entire surface gets remade. Old features are buried under new lava. Whatever geological history existed before is effectively erased. This model emerged from careful study of how planets lose heat under extreme atmospheric conditions. Computer simulations of planetary interiors showed that a world without plate tectonics, trapped beneath an insulating blanket of carbon dioxide, would inevitably accumulate internal pressure until catastrophic release became unavoidable. The physics of heat transport and crustal mechanics pointed toward this boom and bust cycle as the only plausible explanation for Venus's unique volcanic character. The evidence for this is written in the age of the Venusian surface itself. When the Magellan spacecraft mapped Venus using radar in the early 1990s, it found something striking. The surface of Venus is remarkably uniform in age. Most of it appears to be around 500 million years old, give or take. That kind of uniformity is deeply unusual. On Earth, surface ages vary enormously. Some ancient continental cratons are several billion years old, while ocean floors are geologically young. On Venus, almost everything looks the same age. The most straightforward explanation is that the planet underwent a catastrophic resurfacing event roughly 500 million years ago, wiping the geological slate clean across most of its surface. Whatever came before is gone. That raises an unsettling implication. If the last resurfacing happened 500 million years ago, and these events are driven by the buildup of heat that has no other escape, then Venus may be building toward another one right now. Heat has been accumulating for 500 million years. The internal pressure is growing. At some point, and no one can say exactly when, another catastrophic resurfacing may begin. The entire surface, slowly building its volcanic record over hundreds of millions of years, could eventually be buried again. But here's something the Magellan data also suggested. Venus might not be waiting for a full-scale resurfacing event. Some volcanic activity may be happening right now. Magellan detected regions that looked geologically fresh, lava flows that appeared smoother and less cratered than surrounding terrain, suggesting they were younger. The evidence wasn't conclusive at the time. Radar images can only tell you so much. Scientists have refined these observations using crater counting techniques, which analyze the density of impact craters across different regions to estimate surface age. Older surfaces accumulate more craters over geological time. The uniformity in crater density further supported the recent resurfacing hypothesis, while also hinting at ongoing activity in scattered locations. More recent analysis has pushed that case further. Scientists re-examining Magellan data found specific volcanic vents on Venus where the shape of the vent opening changed between radar passes, separated by just a few months in 1991. Vents don't change shape on their own. The most reasonable explanation is volcanic activity, fresh eruptions that reshaped the vent during the time Magellan was observing. If that interpretation is correct, then Venus was actively erupting while a spacecraft was orbiting above it. Other evidence points in the same direction. The sulfur dioxide levels in Venus's upper atmosphere fluctuate over time. Sulfur dioxide is produced by volcanic eruptions. On Venus, it feeds the sulfuric acid cloud system that blankets the planet. Spikes in sulfur dioxide concentration detected from orbit align with what you'd expect if fresh volcanic outgassing events were injecting new material into the atmosphere. The chemistry of Venus's clouds may be directly connected to ongoing eruptions happening right now on the surface below. Mont Mons is probably the most famous example. It's one of the largest volcanoes on Venus, a shield volcano rising about 8 kilometers above the surrounding plains. Analysis of infrared data collected by the European Space Agency's Venus Express mission found that certain areas near Mont Mons showed changes in surface emissivity consistent with fresh lava flows. The material appeared to have been erupted sometime within the past few years or decades. That's an extraordinarily short window in geological terms. It suggests that Mont Mons is not just a large volcano, it may be an active one. This changes how we think about Venus. For a long time, the standard picture was of a geologically frozen world, a surface baked into place 500 million years ago, and sitting there unchanged ever since, preserved under crushing pressure and brutal heat. That picture isn't quite right. Venus appears to be geologically alive, churning internally, venting heat through volcanic activity that contributes sulfur dioxide to its atmosphere, reshapes its surface, and connects the planet's interior to its toxic chemistry in direct, ongoing ways. What the volcanoes of Venus tell us, more than anything else, is that the planet is not static. It's a world under pressure, literally and geologically. The heat inside it has to go somewhere, and the surface shows where it goes. Lava plains that cover most of the lowlands, corona structures that form when plumes of hot mantle material push up against the crust from below, shield volcanoes built up over long eruption histories, and regions where that eruption history may not be history at all, but present tense. And there's growing evidence that some of them are still active right now, still pushing fresh lava across a surface that has been reshaped by fire more times than we can count. The first spacecraft humanity ever sent to land on another planet's surface didn't survive long enough to tell us anything. That's not a metaphor. That's not an exaggeration. The probe was destroyed before it could send back a single reading from the surface of Venus, crushed by conditions that engineers on Earth hadn't fully understood. And it wasn't the last time that would happen. The story of the Soviet Venera program is one of the most remarkable chapters in the history of space exploration. It is a story of repeated failure, gradual understanding, and eventually hard-won success, all in the pursuit of a planet that seemed almost determined to remain unknown. The program began in 1961. The Soviet Union launched Venera 1 that year, intending it to fly past Venus and take readings from close range. It never arrived. Contact with the spacecraft was lost before it reached its destination, somewhere in the void between Earth and Venus. There was no data. There was no flyby. There was nothing. It was an early reminder that getting to Venus was not going to be simple, but the Soviets kept going. That persistence across decades and dozens of missions is what makes the Venera program worth understanding. Venera 3 reached Venus in March of 1966. It did something no human-made object had ever done before. It made contact with another planet's surface. Think about that for a moment. For the first time in history, something built by human hands actually reached the ground of another world. But Venera 3 was crushed during descent. The atmospheric pressure was far greater than the spacecraft had been built to withstand. It hit the surface, and it was destroyed. No data came back. The achievement was real, but the information wasn't. The Soviets had gotten there. They just couldn't survive there. Venera 4 launched in 1967. This time, the probe was built to transmit data while descending through the atmosphere. It worked for a while. Venera 4 sent back readings as it fell through the Venusian clouds: temperature, pressure, atmospheric composition. Real data for the first time from inside Venus's atmosphere. But Venera 4 never reached the surface either. The probe was designed to withstand pressures up to about 25 atmospheres. The actual pressure on Venus is 92. The spacecraft was crushed somewhere in the lower atmosphere, well before it reached the ground. The data it returned was extraordinary, but it also revealed something unsettling. The Soviets had massively underestimated just how extreme Venus really was. That realization forced a complete rethinking. The probes being sent to Venus weren't nearly strong enough. The atmosphere was far denser, far deeper, and far hotter than early models had suggested. If you were going to land something on Venus and actually have it survive, you had to build something radically different. Something that could handle pressures and temperatures that seemed almost impossible by engineering standards. The scale of this challenge became clearer with each failed mission. Venus wasn't just a little hotter or a little denser than expected. It was fundamentally more hostile than any planetary environment humanity had yet attempted to reach. The engineers had to rethink nearly every assumption. The heat shields needed to be stronger. The atmospheric braking systems needed to be more efficient. The entire structural design of the spacecraft needed reinforcement. It was becoming clear that reaching Venus wouldn't just require incremental improvements to existing designs. It would require a fundamental shift in how Soviet engineers approached landing on other worlds. The Soviets went back to work. Venera 7 launched in 1970. It was built to withstand 180 atmospheres, nearly twice the actual pressure on Venus's surface, just to be safe. It could handle temperatures up to 540 degrees Celsius. The engineers had overcorrected deliberately. They weren't going to get caught underestimating Venus again. Venera 7 landed on December 15, 1970. And it survived. For 23 minutes, it transmitted data from the surface of another planet. Temperature readings, pressure readings, confirmation that it had actually landed. 23 minutes. Then it went silent. But those 23 minutes were historic. That transmission was the first time humanity had ever received data from the surface of another planet. Not flyby data, not atmospheric data, surface data from the ground of Venus itself. 23 minutes doesn't sound like much. By any ordinary measure, it isn't. But think about what it took to get there. A decade of failed missions. Probes crushed, probes lost, probes destroyed by conditions that the engineers hadn't anticipated. Venera 7 was the result of all of that failure, absorbed and learned from. It landed on the most hostile surface in the solar system and talked to Earth for 23 minutes before the heat and pressure finally won. That's not a failure. That's one of the greatest engineering achievements in the history of spaceflight. The program continued. Venera 8 landed in 1972 and transmitted for 50 minutes. Then came Venera 9 and Venera 10 in 1975, and these missions did something that hadn't been done before. They returned images, not measurements, not data tables, actual photographs from the surface of another planet. The images showed a landscape that surprised almost everyone. Angular rocks, sharp edges, slabs of stone that hadn't been worn smooth the way erosion would smooth them on Earth. There was no water erosion on Venus, no wind erosion significant enough to round the rocks off. The landscape looked almost freshly made, geologically recent. The images also showed something else. The sky above the surface had a kind of dim, orange-tinted light, filtered through the thick cloud layers far above. It wasn't dark. It wasn't bright. It was something in between, a haze that made the surface feel strangely enclosed, like the bottom of something. These photographs transformed humanity's understanding of Venus from abstract data into concrete visual reality. Scientists could now see the actual terrain, the texture of the rocks, the way shadows fell under the filtered sunlight. The revelation that Venus's surface was covered in angular, unweathered rock fundamentally changed geological thinking about the planet. It suggested a much younger surface than many theorists had anticipated, one shaped by volcanic activity rather than by the slow erosion processes familiar from Earth. The images became iconic symbols of Soviet achievement in space exploration, proof that robotic explorers could survive and function in environments that seemed almost impossibly harsh. Venera 13 landed in March of 1982. By this point, Soviet engineers had refined the lander design significantly through years of iteration. The probe was equipped with cameras, drills, and scientific instruments. It landed, it stabilized, and it started transmitting. Color photographs came back, the first color images ever taken on another planet's surface. The surface appeared orange-brown under the filtered light. Flat slabs of basaltic rock covered the ground around the lander. The images were sharper and richer than anything returned before. Venera 13 also drilled into the surface and analyzed the rock composition directly. It was performing real science in real time from the surface of Venus. Then, after 127 minutes, it went silent. The heat and the pressure had finally overcome the engineering, but 127 minutes was enough. Venera 13 returned more data from Venus's surface than any lander before or since. The entire Venera program spanned more than 2 decades. It included more than a dozen missions to Venus. Some were lost in transit, some were crushed, some landed and transmitted for minutes, some lasted longer. Each mission taught the engineers something that the previous one hadn't. The whole program was a process of learning what Venus actually was, not what models suggested it might be, but what it actually physically was. A place with pressure that destroyed early probes outright. A place with temperatures that overwhelmed every early heat shield design. A place that defeated spacecraft after spacecraft until the engineers understood it well enough to build something that could briefly hold on. What the Venera program demonstrated more than anything is that Venus doesn't yield information easily. Every reading, every photograph, every data point came at an enormous cost in engineering, in effort and in failed attempts. The Soviets lost probes on the way there. They lost probes in the atmosphere. They lost probes the moment they hit the surface. They kept going anyway. They rebuilt. They recalculated. They reinforced. And gradually, over 2 decades of trying, they pulled back a picture of a planet that had been completely hidden behind its clouds. The images Venera returned, the temperature readings, the pressure readings, the rock composition data, all of it came from spacecraft that were essentially on borrowed time from the moment they touched down. They were not built to last. Nothing built by humans has ever lasted on Venus for long. Venera 13 lasted 127 minutes on the surface of Venus, and that is still the record decades later for any human-made object on the most hostile surface we've ever tried to reach. Earth is wrapped in an invisible shield that most people never think about. It's not something you can see, it's not something you can feel, but without it, Earth would be a very different place. The solar wind is a constant stream of charged particles flowing outward from the sun in every direction. Protons, electrons, helium ions, they travel at speeds of around 400 kilometers per second, and they hit everything in their path. Earth's magnetic field deflects most of that stream. It bends the solar wind around the planet, creating a protective bubble called the magnetosphere that extends tens of thousands of kilometers into space. Life on Earth exists partly because of that bubble. Venus doesn't have one. To understand why that matters, you have to understand where Earth's magnetic field comes from. Deep inside the planet, below the solid iron inner core, there is a layer of liquid iron and nickel. This outer core is in constant motion. The rotation of Earth drives convective currents through that liquid metal, and those moving electrical charges generate a magnetic field. It's essentially a planetary dynamo, a generator the size of a world, running continuously for billions of years. The field it produces isn't perfectly uniform. It shifts over time. It's weakened in places. But it's always there, always deflecting the solar wind, always protecting the atmosphere above. Venus has an iron core too. The planet is nearly identical to Earth in size and density. Its interior structure is believed to be broadly similar. So why doesn't Venus have a magnetic field? The answer almost certainly comes down to one thing: rotation. Venus rotates extraordinarily slowly. One full rotation takes 243 Earth days. That's longer than a Venusian year, which is only 225 Earth days. Venus takes longer to spin once than it takes to complete an entire orbit around the Sun. And on top of that, it rotates backwards. If you were looking down at the solar system from above, most planets spin counterclockwise. Venus spins clockwise. Slowly, backward, and for reasons that aren't fully settled, it spins at all. That sluggish rotation is almost certainly why Venus has no planetary dynamo. The convective motion in a planet's liquid core needs to be organized by rotation to generate a sustained magnetic field. Earth's rotation provides that organizing force. It drives the currents in the liquid outer core into patterns that sustain the magnetic field over geological timescales. Venus rotates so slowly that those organizing forces are essentially absent. The liquid iron in its core may circulate, but not in a way that generates and sustains a global magnetic field. The dynamo never got started, or if it did, it stopped a very long time ago. Without a magnetic field, Venus is exposed. The solar wind hits the planet's upper atmosphere directly. Now, Venus isn't completely unprotected. The sun's ultraviolet radiation ionizes the uppermost layers of Venus's atmosphere, creating what's called an ionosphere, a region of electrically charged gas. That ionosphere interacts with the solar wind and creates what scientists call an induced magnetosphere. It's a magnetic environment that forms from the outside in, generated by the interaction between the solar wind and the ionosphere, rather than by anything happening inside the planet. It provides some deflection. Some of the solar wind gets diverted around Venus rather than plowing straight through, but it's a far weaker barrier than what Earth has. Think of Earth's magnetosphere as a thick stone wall and Venus's induced magnetosphere as a chain-link fence. Both stop some things. They don't stop the same things. The consequences play out over geological time. The solar wind that makes it past Venus's limited defenses collides with atmospheric particles in the upper layers. When it hits water vapor molecules, those molecules can be broken apart. A water molecule is one oxygen atom and two hydrogen atoms. The hydrogen atoms are light, the lightest atoms that exist. Once they're freed from the water molecule and exposed to the solar wind at the top of the atmosphere, they can be accelerated and swept away into space. The oxygen, being much heavier, tends to stay behind. This process is called atmospheric sputtering and ion escape, and it has been happening on Venus continuously, probably for billions of years. What that means for Venus's history is significant. Early Venus, as we've covered, likely had liquid water, possibly oceans that persisted for 1 billion years or more. As the planet warmed and more water vapor entered the atmosphere, some of that vapor reached high altitudes. There, ultraviolet radiation and the solar wind went to work on it. The water molecules were split, the hydrogen escaped. The oxygen reacted with surface rocks or lingered in the atmosphere. Over time, that process drained the planet of its water. Not all at once. Gradually, continuously. One hydrogen atom at a time. The European Space Agency's Venus Express mission, which orbited Venus from 2006 to 2014, measured this process directly. It detected hydrogen and oxygen escaping from Venus's atmosphere into space, with roughly twice as many hydrogen ions escaping as oxygen ions, almost exactly the 2-to-1 ratio you'd expect if water were being broken apart and the hydrogen stripped away. The escape is happening right now. The solar wind is still eroding Venus's atmosphere as you're watching this. What's left of Venus's water is disappearing incrementally into space. The connection between the missing magnetic field and the missing oceans is one of the most important threads in understanding how Venus became what it is. It's not just the greenhouse effect in isolation. It's not just the volcanic outgassing in isolation. The lack of magnetic protection means that as Venus heated up and water vapor rose into the atmosphere, there was nothing to stop the solar wind from dismantling those molecules and carrying the hydrogen away. On Earth, the magnetosphere intercepts much of the solar wind before it can reach the upper atmosphere. Water vapor that makes it to high altitudes on Earth still faces some ultraviolet dissociation, but the rate of hydrogen escape is drastically lower than on Venus. Earth holds on to its water. Venus couldn't. There's a deeper question here that planetary scientists are still working through. Did Venus ever have a magnetic field? The planet may have had one in its early history when its interior was hotter and more active. If it did, that early field may have protected early Venus long enough for oceans to form and persist. As the interior cooled, or as rotation slowed, and Venus may have been slowed by gravitational interactions with the Sun and Earth over billions of years, the dynamo could have weakened and eventually stopped. When the shield came down, the solar wind took over, and the planet that might have been habitable began its long transformation into the world the Venera probes encountered. That's not a small detail. The presence or absence of a magnetic field may be one of the fundamental factors that determines whether a rocky planet stays habitable or loses that status over geological time. We look for magnetic fields as one of the indicators of habitability when we study planets beyond our solar system. Venus tells us why that matters. Venus has no such shield, And the solar wind has been stripping away its lighter atmospheric components, including the hydrogen that was once part of its oceans, for billions of years without anything to stop it. Venus rotates so slowly that its day is longer than its year. That sentence sounds like a mistake. It isn't. Venus takes 243 Earth days to complete one full rotation on its axis. It takes only 225 Earth days to orbit the Sun, so the planet finishes its trip around the Sun before it finishes spinning once. Think about what that means. A year passes on Venus before a single day does. Most people don't register how strange that is when they first hear it. We take for granted that a day and a year are on roughly the same timescale. Earth's day is 24 hours. Earth's year is 365 of those days. The two numbers live in the same universe of comprehension. On Venus, the relationship is inverted entirely. The planet barely rotates. It just crawls through space at this almost imperceptible spin, slower than any other planet in the solar system. And yet, if you could somehow look down at Venus from above its cloud tops, you would see those clouds moving. Fast. The upper atmosphere of Venus doesn't rotate once every 243 days. It races around the planet in about 4 Earth days. 4. The atmosphere is lapping the planet beneath it roughly 60 times over. That gap between the near stillness of the planet and the velocity of its sky is one of the most bizarre things we've found anywhere in the solar system. Astronomers call it atmospheric superrotation. The wind speeds at the cloud tops are around 360 kilometers per hour. For context, that's comparable to the sustained wind speeds in a Category 5 hurricane, the most powerful storms on Earth, systems that devastate coastlines and flatten cities, rotate at wind speeds that Venus matches and exceeds in its everyday upper atmosphere. And this isn't a temporary storm. It isn't a seasonal pattern. It's the permanent state of Venus's atmosphere, circling endlessly, year after year, decade after decade. The puzzle is how this happens. When you think about how an atmosphere should behave, the basic expectation is that it moves roughly with the planet beneath it. Friction between the surface and the lower atmosphere transfers some of the planet's rotational motion upward. Thermal gradients, the difference in temperature between sunlit and shadowed hemispheres, drive circulation. The Coriolis effect produced by the planet's rotation shapes how wind systems organize themselves. All of these forces should, in principle, keep the atmosphere reasonably coupled to the surface. On Venus, none of that adds up to superrotation. The planet spins so slowly that the Coriolis effect is almost negligible. The temperature difference between day and night sides is minimal. This was because the thick atmosphere distributes heat so effectively around the entire planet. There's no obvious mechanism that should be pumping the atmosphere to 60 times the planet's rotational speed and then holding it there indefinitely in a steady state. It shouldn't work. And yet it does. Several explanations have been proposed over the years. One involves the way solar energy is absorbed at different altitudes within the atmosphere. Different layers absorb different wavelengths of radiation. The heating patterns that result could potentially drive momentum upward from lower atmospheric layers into higher ones. Another involves atmospheric waves, patterns of pressure variation that travel through the atmosphere and can transfer angular momentum from one region to another. There's also the possibility that the slow rotation itself is part of the answer, that the very absence of a strong Coriolis effect allows wind patterns to organize in ways that would be disrupted on a faster spinning planet. But no single explanation has been accepted. None of them fully account for what we observe. This isn't a gap in knowledge that scientists haven't thought about. It's a problem they've worked on for decades and haven't resolved. Venus's superrotation remains genuinely unexplained. Now contrast those upper atmosphere winds with what's happening at the surface. Down near the ground, the wind barely moves. Surface winds on Venus are estimated at roughly 2 to 3 meters per second. That's a light breeze by Earth standards. You wouldn't even need to hold your hat. If you were standing on Venus, which for reasons covered earlier in tonight's discussion, you absolutely cannot do, the wind would barely be noticeable. It certainly wouldn't be blowing you off your feet. But here's what most people don't realize about that gentle breeze. The lower atmosphere of Venus is extraordinarily dense. The pressure at the surface is 92 times Earth's sea level pressure. That pressure corresponds to an atmosphere that is thick in a way that Earth's air simply isn't. The density of Venus's surface atmosphere is nearly comparable to that of liquid water. So when wind moves through it, even slowly, the force it carries is enormous. A 2 meter per second wind on Venus doesn't feel like a breeze on Earth. It pushes more like a slow-moving river current. The momentum in that air, at that density, is something our intuitions about wind are completely unprepared for. The Venera landers that survived long enough to send data back reported surface winds that sounded gentle by any normal standard. But those winds were pushing against dense, thick atmosphere that carried far more physical force than the numbers suggest. The superrotation also has a direct effect on the uniformity of Venus's cloud cover and temperature distribution. Because the upper atmosphere is constantly cycling around the planet at high speed, heat gets redistributed efficiently. There's no meaningful difference in temperature between the equator and the poles at cloud level. There's very little variation between day and night sides at altitude. The super-rotating atmosphere acts like a giant blender, smoothing out the temperature gradients that would otherwise develop. This is part of why Venus looks so featureless from a distance. The cloud tops are a uniform, bright, unchanging sheet. The underlying dynamics are violent, but the visible result is almost placid. It also means that Venus's cloud system lacks the kind of large-scale organized storm structures we see on Jupiter or Saturn. Jupiter has bands and cyclones driven by its fast rotation and strong Coriolis forces. Saturn has a hexagonal polar vortex produced by wave interference under specific rotational conditions. Venus's slow spin and fast atmosphere produce something different, a relatively uniform overcast, disturbed by smaller patterns and the dark UV absorbing streaks that have puzzled scientists. But nothing like the grand storm systems of the outer planets. What we're left with is a planet whose surface barely moves and whose sky never stops. 243 days to complete a single spin. Up above, the clouds have gone around 60 times in the same period. The superrotation is still not fully explained. It's one of those fundamental mysteries about Venus that tells us we don't yet understand the atmospheric physics of the planet as well as we'd like to think. 50 kilometers above the surface of Venus, something remarkable happens to the conditions. The heat drops, the pressure eases, and if you were floating at that altitude, roughly 50 to 65 kilometers above the hellscape below, the temperature around you would range from about 30 to 70 degrees Celsius. That's warm, uncomfortably warm by human standards, but it's the kind of warm where liquid water can exist. It's the kind of warm where life, as we understand it, is not automatically impossible. The atmospheric pressure at that altitude sits close to what you'd experience standing at sea level on Earth. Not 92 times greater, not crushing, just air. Something close to normal. Think about that for a moment. In the same atmosphere that produces sulfuric acid rain and traps heat to nearly 500 degrees at the surface, there is a band of sky that is, by two of the most critical measurements for life, more Earth-like than the surface of Mars. Mars gets most of the attention when we talk about habitable worlds and future exploration, but the surface of Mars is cold enough to freeze carbon dioxide, thin enough that radiation passes straight through to the ground, and dry enough that liquid water can't persist. The cloud layer of Venus, by contrast, sits at temperatures and pressures that extremophile bacteria on Earth would not find unusual. Not comfortable, not ideal, but not immediately fatal. Most people don't realize this. When we say Venus is the most hostile planet we know, we mean the surface. The sky above Venus is something else entirely. Now, this doesn't mean Venus's upper atmosphere is actually habitable. The clouds are made of sulfuric acid. We need to be clear about what that means. Sulfuric acid at 75 to 98% concentration, and that's the range measured in Venus's cloud droplets, is among the most corrosive substances we know. Battery acid is about 30 to 50% sulfuric acid. Industrial processes that use concentrated sulfuric acid require extreme handling precautions, specialized equipment, and strict safety protocols. Nothing known to science survives in 98% sulfuric acid. Not bacteria, not archaea, nothing. The chemistry simply doesn't allow for it. And yet, astrobiologists haven't closed the door entirely. That's the thing about this question. It refuses to stay settled. Here's what makes it interesting. Sulfur-based chemistry can, in theory, produce molecular structures capable of forming a protective shell around a cell. Ring-shaped arrangements of sulfur atoms are known to exist in Venus's atmosphere. Researchers have proposed that these sulfur rings could coat a microbial cell, shielding it from the acid surrounding it, and simultaneously absorbing ultraviolet radiation, which is intense in the upper atmosphere, and re-emitting it at longer, less damaging wavelengths. It's a specific, chemically grounded hypothesis. Not science fiction, not wishful thinking. An actual proposed mechanism based on sulfur chemistry that we know is present on Venus. What makes this hypothesis harder to dismiss is that something in Venus's clouds is already absorbing ultraviolet light and re-radiating it at different wavelengths. We can see it. For decades, astronomers studying Venus in ultraviolet light have observed dark streaks running through the cloud layers. These streaks are persistent. Hurricane-force winds in the upper atmosphere tear across the planet, and these dark patches remain coherent anyway. They shift and move, but they don't dissolve. They hold their shape in conditions that should scatter and disperse any simple chemical particulate within days. They absorb UV radiation in a pattern consistent with a substance specifically suited to capturing ultraviolet light. And when scientists have analyzed the particle sizes responsible for these streaks, they fall roughly within the range of a micron in length, approximately the size of a bacterium. Downty. Let's be careful here. Size alone means almost nothing. Lots of chemical particles are about a micron across. Iron chloride particles are one candidate. Certain sulfur compounds are another. There are plausible abiotic explanations for every individual characteristic of these streaks. No single measurement points unambiguously to life, but the combination of characteristics, the UV absorption pattern, the persistence in extreme wind, the particle size, the sulfur chemistry, has been enough for serious scientists to keep the question open. Then 2020 happened, and the question got considerably louder. A team of astronomers announced in September of that year that they had detected phosphine in Venus's atmosphere. Phosphine is a molecule, one phosphorus atom bonded to 3 hydrogen atoms. On Earth, it's produced by certain anaerobic microbes and by industrial processes. In the outer solar system, it forms naturally under the extreme conditions inside gas giants like Jupiter. But on Venus, neither of those sources should apply. There are no gas giant scale pressures to produce phosphine abiotically. There are no known industrial sources, and the team claimed to have detected it at concentrations far above what any known chemistry on Venus could produce. The implication, stated carefully by the researchers themselves, was that something was producing phosphine that their models couldn't account for. They were not claiming to have found life. They were claiming to have found an anomaly. But phosphine, in Venus's conditions, with no obvious abiotic source, is exactly the kind of anomaly that astrobiologists call a biosignature candidate. The scientific community responded fast. Within weeks, other researchers were scrutinizing the data. The original detection had used two separate telescopes, the James Clerk Maxwell Telescope in Hawaii and the ALMA array in Chile. The ALMA data, it turned out, had a processing error. When that error was corrected, the phosphine signal dropped substantially. Some researchers argued it dropped to levels consistent with background noise. Others maintained there was still a real signal, just weaker than originally reported. The debate spread to whether the spectral line used to identify phosphine could be confused with sulfur dioxide, which is abundant on Venus and produces a signal in a similar region. The team behind the original paper has defended their findings through multiple revisions. Other teams have published analyses reaching different conclusions. As of now, the phosphine question is unresolved. The detection has neither been confirmed nor definitively disproved. It remains what it became on the day of publication, a controversy that forced planetary scientists and astrobiologists to take Venus's upper atmosphere more seriously than most had been taking it before. What makes the phosphine story significant isn't just the specific molecule. It's what it revealed about how little attention the scientific community had paid to Venus as an astrobiology target. Mars has received rover after rover. Enceladus and Europa get discussed constantly as potential hosts for subsurface ocean life. Venus, for most of the last few decades, was treated as a dead end. Too hot, too hostile. Nothing worth investigating biologically. The phosphine announcement forced a reassessment. Suddenly, the cloud layer was worth studying. Suddenly, the dark UV-absorbing streaks mattered more. Suddenly, the question of what's actually floating around in that sulfuric acid haze 50 kilometers above the surface became a serious research priority. NASA has funded studies into the feasibility of life in Venus's clouds, not as a fringe project, as legitimate astrobiology research. The hypothesis is considered scientifically credible enough to warrant investigation, even if the probability remains low and the obstacles remain massive. The obstacles are massive. Even the best-case scenario for Venusian cloud life involves organisms that would need to survive indefinitely in concentrated sulfuric acid, maintain altitude in a dynamic and turbulent atmosphere, generate energy from chemistry that doesn't map onto any known biological pathway, and reproduce under conditions that destroy every molecule we know of as biochemically essential. Water, as liquid water, can't persist in concentrated sulfuric acid. DNA and proteins as we know them would degrade almost immediately. If life exists in Venus's clouds, it would have to be so fundamentally different from anything we've studied on Earth that we might not recognize it as life at all. And yet, the conditions for temperature and pressure exist. The energy source in ultraviolet radiation exists. The chemical substrates in the form of sulfur compounds exist. Life on Earth has appeared in volcanic vents, in hypersaline pools, in ice sheets, in pH extremes that chemists once considered incompatible with biology. Every time we've expanded the definition of where life can survive, life has already been there. Whether those dark streaks are chemistry or biology, we genuinely don't know. And that uncertainty, sitting 26 million miles away in a sulfuric acid cloud, is one of the most intriguing open questions in astrobiology. Venus doesn't have anything to do with us until you start thinking about it carefully. It sits there in the night sky, bright and distant, and most people assume it's someone else's problem. Another planet, another story. But Venus is the only planet in our solar system that we know of where a greenhouse effect ran completely out of control and locked the entire world into a state of irreversible catastrophe. That's not someone else's problem. That's directly relevant to the chemistry happening in our own atmosphere right now. The greenhouse effect itself is not the villain here. Earth has one. It's the reason our planet stays warm enough to support liquid water. Without any greenhouse effect at all, Earth's average surface temperature would sit around negative 18 degrees Celsius, frozen, lifeless. The greenhouse effect is part of why we exist. Carbon dioxide, water vapor, methane, these gases trap heat that would otherwise radiate out into space, and that trapped heat is what keeps the surface of this planet in a range compatible with life. The problem isn't the greenhouse effect. The problem is what happens when it runs away. On Venus, it ran away. And once it started, nothing stopped it. Water evaporated from the surface. That water vapor entered the atmosphere and trapped more heat. Higher temperatures caused more evaporation. The cycle fed itself. Eventually, the oceans were gone. Ultraviolet radiation split the remaining water molecules in the upper atmosphere. The hydrogen escaped to space. And with no water left, the carbon cycle collapsed entirely. On Earth, carbon dioxide gets pulled out of the atmosphere by rainfall, which reacts with surface rocks and locks carbon into mineral form. Venus lost that mechanism. Volcanic outgassing kept pumping carbon dioxide into the atmosphere with nothing to remove it. The temperature climbed, the greenhouse effect strengthened, and the planet arrived at where it is today, 465 degrees Celsius at the surface with no way back. That's what a runaway greenhouse effect looks like when it's finished. Scientists are careful about making direct comparisons between Venus and Earth's current climate situation. The mechanisms are not identical. The timescales are different. Venus's transformation was driven by its position slightly closer to the Sun, by the early brightening of the young Sun, by the loss of its magnetic field, by geological factors that don't map cleanly onto what's happening here. Earth is not on a trajectory to become Venus. That's not what this comparison is about. But Venus demonstrates something important. It demonstrates that the line between habitable and uninhabitable is not a wide, forgiving margin. It demonstrates that planetary climate systems can reach thresholds that, once crossed, are not recoverable on any timescale that matters. The feedback loop that consumed Venus didn't reverse. The oceans didn't return. The carbon dioxide didn't come back out of the atmosphere. What happened to Venus stayed, and that tells us something meaningful about how planetary systems behave at their limits. Earth has stabilizing mechanisms that Venus lacked or lost too early. The first is plate tectonics. Earth's crust is broken into plates that move slowly over geological time, driven by convective currents in the mantle below. This process continuously recycles the crust, pulling surface rock down into the interior and pushing new rock up at mid-ocean ridges. Carbon dioxide that gets locked into carbonate rocks at the surface eventually gets pulled into the interior through subduction zones and released back through volcanic activity. It's a cycle, a thermostat of sorts. Venus, as far as we can tell, doesn't have active plate tectonics. Its heat escapes through a different mechanism, catastrophic volcanic resurfacing events that are violent and geologically brief rather than the slow, steady cycling that operates on Earth. Without that carbonate-silicate cycle, Venus had no long-term mechanism for pulling excess carbon dioxide out of the atmosphere. The second stabilizing mechanism Earth has is liquid oceans. The oceans absorb enormous quantities of carbon dioxide directly from the atmosphere. They also drive the chemical weathering processes that lock carbon into minerals. They moderate temperature swings. They're part of the carbon cycle in ways that are fundamental and not easily replaced. Venus lost its oceans when the runaway warming began. Once they were gone, all the things oceans do for planetary stability went with them. The third difference is Earth's magnetic field. Venus, rotating as slowly as it does, never generated the internal dynamo that produces a global magnetic field. Without that field, solar wind has been stripping lighter elements from Venus's upper atmosphere for billions of years. Earth's magnetic field is part of why we still have the atmosphere we do. It's part of why we still have water. It's not a dramatic, visible thing. Most people go their entire lives without thinking about it. But it's one of the reasons Earth remained habitable while Venus did not. And then there's distance. Earth orbits at 1 astronomical unit from the Sun. Venus orbits at about 0.72. That difference sounds small, but it placed Venus close enough to the Sun that as the early Sun gradually brightened over geological time, Venus received just enough additional energy to tip into instability. Earth, sitting slightly farther out, stayed within the range where liquid water remained stable at the surface. The habitable zone is a real thing, not just a loose concept, and Venus's history is part of the evidence for where its edges actually are. What all of this means is that Earth isn't just lucky. Earth has multiple overlapping systems that resist the kind of catastrophic tipping point Venus experienced. Plate tectonics, oceans, a magnetic field, a slightly more favorable orbit. These things work together to keep the planet within a range compatible with life. None of them are infinite, none of them are unconditional, but together they've maintained stability for roughly 4 billion years. And understanding that stability, understanding which factors matter, how robust they are, what their limits are, requires a comparison case. Venus is that comparison case. Climate scientists use Venus directly in the models they build, not as a prediction of Earth's future, but as a boundary condition, a real-world example of what a greenhouse effect looks like when it goes as far as it can go. When researchers model the behavior of carbon dioxide in Earth's atmosphere, or the relationship between water vapor and temperature, or the dynamics of the carbon cycle under different conditions, having an actual planetary example of the extreme outcome helps calibrate those models. Venus gives us a fixed point on the far end of the spectrum. We know what happens at the extreme. Now we can understand the range better. There's a version of thinking about Venus that goes something like this. It's a dead world, baked and crushed, nothing to do with us, a curiosity. And there's another version that recognizes Venus as the most informative natural experiment on planetary climate that we have access to. Both planets formed from the same material. Both had carbon dioxide. Both had water. One has life, liquid oceans, breathable air. One has a surface hot enough to melt lead. The question of why they diverged is not a purely academic one. It has direct implications for how we understand the systems that keep Earth within the range where we can exist. Venus isn't a warning in the sense of a direct prediction. Earth is not Venus. The situations are not the same, and treating them as equivalent would misrepresent the science. But Venus is a demonstration. It demonstrates that greenhouse effects have no natural ceiling if feedback loops are allowed to run. It demonstrates that habitability depends on a specific combination of conditions, not just proximity to a star. It demonstrates that climate systems can cross thresholds that can't be undone. We understand the greenhouse effect better. We understand planetary tipping points better. We understand the conditions for habitability better. All because Venus exists and we can study what went wrong there. We've been sending spacecraft to Venus since 1961. By the standards of what we still don't know, we've barely started. Think about that for a moment. Dozens of missions, decades of observations. And there are still questions about Venus so fundamental that we can't answer them with any confidence. We don't know if it's geologically active right now. We don't know what exactly happened to its water. We don't fully understand the history of its climate. We can't explain the dark streaks in its clouds. For a planet that's our closest neighbor, sometimes only 26 million miles away, that's a remarkable amount of ignorance. And it tells you something important about how difficult Venus actually is to study. The next wave of missions is designed to start closing those gaps. NASA selected 2 Venus missions in 2021. The first is called Da Vinci Plus, which stands for Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging. The concept is straightforward but technically demanding. A probe drops into the atmosphere and descends all the way to the surface, spending about an hour falling through the cloud layers and the dense lower atmosphere, sampling gases as it goes. It's measuring the chemical composition of the atmosphere at different altitudes. It's looking for noble gases, elements like argon and neon that don't react with anything and therefore preserve a record of the atmosphere's original composition. Those noble gas signatures can tell scientists what Venus's atmosphere looked like billions of years ago and how it's changed. Da Vinci Plus will also take images on the way down, targeting a highland region called Alpha Regio. It's one of the only missions that will give us close-up visual data from the lower atmosphere of Venus. That alone is something we've never had. The second NASA mission is Veritas, which stands for Venus Emissivity, Radio Science, INSAR, Topography, and Spectroscopy. It's an orbiter, not a lander. It uses radar to see through the permanent cloud cover and map the surface of Venus in far greater detail than anything we've achieved before. The Magellan spacecraft did this in the early 1990s, and it was a revelation. Veritas would do it again with 30 years of technological improvement behind it. The topographic maps it produces would let scientists identify volcanic features, tectonic structures, regions where the crust has been deformed or reshaped. It would let us track whether certain volcanic areas have changed since Magellan mapped them. That would be direct evidence of ongoing geological activity. Veritas would also analyze the mineral composition of the surface by measuring infrared emissions in narrow spectral windows, where the atmosphere becomes slightly more transparent. That's the kind of data that could tell us whether Venus ever had granite, which requires water to form, and therefore whether it once had oceans. The improvements in radar imaging between Magellan and Veritas represent more than just incremental gains. The newer system would achieve roughly 10 times better resolution, allowing scientists to detect geological features smaller than a football field. This level of detail could reveal whether lava plains show evidence of recent flows where fresh material has covered older terrain. Identifying such young features would strengthen the case for an actively dynamic Venus. Then there's the European Space Agency's Envision mission, currently planned for launch sometime in the early 2030s. Envision is designed to study Venus comprehensively, its atmosphere, its surface, its internal structure. It carries a suite of instruments aimed at understanding the relationship between the planet's geological activity and its atmospheric chemistry. One of the central questions Envision is positioned to address is the volcanic sulfur connection. Venus's sulfuric acid clouds are fed by sulfur dioxide outgassed from volcanoes. If Envision detects changes in sulfur dioxide concentrations in the atmosphere over time, that would be evidence of active volcanism happening right now. It would confirm that Venus is not a geologically dead world, but a living, churning planet still reshaping itself. All three of these missions share a common limitation. They're orbiters and one atmosphere probe. None of them land. None of them sit on the surface. And the surface is where the most direct answers would come from. The problem is that no one has built anything capable of surviving on Venus's surface for more than 127 minutes. That record belongs to Venera 13, set in 1982, and nothing has come close since. The heat alone, 465 degrees Celsius, disables conventional electronics within minutes. The pressure crushes structures not specifically engineered to withstand it. The chemical environment corrodes materials. Building a long-duration Venus lander is one of the hardest engineering problems in planetary science. NASA had been working on it. A concept called the Long-Lived In Situ Solar System Explorer, or LLISSE, explores what it would take to keep a lander alive on Venus for weeks or months rather than minutes. Part of the answer involves silicon carbide electronics. Conventional computer chips are made from silicon and they fail above roughly 250 degrees Celsius. Silicon carbide can operate at temperatures well above 400 degrees. It's a fundamentally different material with the electrical properties needed to build circuits that won't simply stop working when the temperature climbs. Engineers have demonstrated silicon carbide chips operating in Venus-like conditions in laboratory settings. That's promising. But building a full computing and communication system from that technology, miniaturizing it reliable enough for a space mission, that's still an open challenge. There's another approach that sounds almost impossible until you understand the reasoning behind it: mechanical computing. Some researchers have explored using mechanisms inspired by old clock technology, gears, levers, physical logic rather than electronic logic, to create systems that operate at high temperatures without relying on semiconductor electronics at all. A mechanical system doesn't care about heat the same way a transistor does. The idea is unconventional, and it's not the primary direction of development, but it illustrates just how seriously engineers are taking the problem. When your environment defeats every standard solution, you look for solutions that aren't standard. What would a long-duration surface mission actually give us? Quite a lot, as it turns out. Direct chemical analysis of the surface rocks. We know from radar imaging and spectroscopy that Venus has different types of terrain, but we don't have ground truth chemical measurements from most of it. A lander sampling rocks in multiple locations would tell us things about Venus's geological history that no orbital instrument can. Seismometers on the surface would detect Venus quakes and volcanic tremors. From those signals, scientists could map the interior structure of the planet, the thickness of the crust, the state of the mantle, whether the core is solid or liquid. We've done this on the Moon and Mars. We've never done it on Venus. The internal structure of Venus, for all practical purposes, remains unknown. A long-lived lander could also document the surface atmosphere over time, pressure fluctuations, temperature variations, chemical changes, in a way that a probe descending for an hour simply cannot. It could watch the sky. It could image the surrounding landscape at intervals and detect whether anything moves or changes. That kind of sustained observation is exactly what's missing from everything the Venera program gave us. Those probes died before they could tell us anything beyond their first frantic minutes of data transmission. Venus is 26 million miles away at its closest. It's been observed by dozens of spacecraft. There are still fundamental questions about it that we can't answer, which is part of what makes it such a compelling target. Mars is cold, dry, and irradiated, and it gets most of the press when people talk about hostile environments in the solar system. And there are reasons for that. Mars is the planet we've actually sent rovers to. It's the planet with colonization proposals attached to it. It's the planet that shows up in science fiction as the next step for humanity. But when you lay out every world in the solar system and compare them honestly, Mars isn't even close to the most dangerous. Not by a significant margin. The most hostile surface we've ever encountered is sitting 26 million miles away, glowing beautifully in the evening sky. Let's go through the competition. Mercury is the obvious first candidate. It's the closest planet to the Sun. Its surface temperature swings between negative 180 degrees Celsius at night and positive 430 degrees Celsius during the day. That's a range of more than 600 degrees within a single Mercurian day. No atmosphere means no protection from solar radiation, no buffer against the temperature extremes. It sounds brutal, but here's what Mercury doesn't have. It has no atmosphere to crush you. The pressure at Mercury's surface is essentially zero. There's nothing pressing in on a spacecraft, nothing corroding its components, nothing chemically hostile in the environment. A lander on Mercury faces extreme temperature swings. It does not face simultaneous pressure, heat, and acid all at once. Mars is actually the gentlest of the inner planets in terms of surface hostility. The average surface temperature is around -60 degrees Celsius. The atmosphere is thin, about 0.6% of Earth's surface pressure, and composed mostly of carbon dioxide. Radiation at the surface is a genuine concern because Mars has no magnetic field and a thin atmosphere that provides little shielding. But none of this kills a rover instantly. Opportunity operated on Mars for nearly 15 years. Curiosity has been driving across the Martian surface for more than a decade. InSight ran a seismic station there for years. The environment is harsh enough that humans would need protection, but it is an environment that our engineering can handle for extended periods. Now move out to the gas giants. Jupiter has no solid surface. There's no place to land, no ground to stand on. You descend through the atmosphere, and as you go deeper, the pressure increases and the temperature rises. The Galileo probe was sent into Jupiter's atmosphere in 1995. It transmitted data for about 57 minutes before the pressure and heat destroyed it, at a depth where the atmospheric pressure was about 23 times Earth's sea level. That's a fraction of Venus's surface pressure. Jupiter's radiation environment in its magnetosphere is genuinely savage. The radiation belts around Jupiter would destroy unshielded electronics and be lethal to humans in short order. But this is radiation in space around Jupiter, not a surface condition. The planet itself is a gas ball. It can't be landed on. Saturn, Uranus, and Neptune present the same basic situation. They're gas and ice giants, no surfaces. Extreme conditions as you descend into the atmosphere, but no single point of concentrated lethality the way Venus's surface is. Then there are the moons. Io, Jupiter's innermost large moon, is the most volcanically active body in the solar system. Its surface is covered in sulfur compounds, lava plains, and active volcanic eruptions. The temperatures in and around its volcanic vents can reach over 1,600 degrees Celsius. That's extraordinary heat in specific locations. But Io's surface pressure is essentially nothing. It has a thin, tenuous atmosphere of sulfur dioxide. The radiation environment around Io is also severe because it sits deep inside Jupiter's radiation belts. Io is genuinely hostile, but it's hostile in ways that are localized and variable. Step away from an active volcanic region on Io and the surface temperature is around -130 degrees Celsius. The threat is concentrated, not total. Europa presents a different kind of danger. Its surface temperature hovers around -160 degrees Celsius. Its surface is mostly water ice. The intense radiation from Jupiter's magnetosphere bombards the surface constantly, making it one of the highest radiation environments of any solid surface in the solar system. A human standing on Europa's surface without protection would receive a lethal radiation dose in a matter of hours. That's serious. But again, the atmospheric pressure is negligible. Europa doesn't crush things. It doesn't melt them. It irradiates them. Titan is the most intriguing of the moons from a habitability perspective, though not in a way that makes it comfortable. Its thick nitrogen atmosphere means it has surface pressure about 1.5 times that of Earth, genuinely substantial. Its surface temperature is around -179 degrees Celsius. It has lakes and seas of liquid methane and ethane. A human on Titan would need a pressure suit and extraordinary cold protection. But they wouldn't be crushed. They wouldn't be melted. The environment is deeply hostile to life as we know it, but it's hostile in ways that are manageable compared to what Venus does. So what makes Venus different from every one of these worlds? It's not that Venus does one thing worse than all of them. It's that Venus does everything at once. The surface pressure is 92 times Earth's sea level. That alone would destroy a spacecraft not specifically engineered to handle it. The temperature is 465 degrees Celsius, not in volcanic hotspots, not seasonally, not at one particular latitude, but everywhere, all the time, at every point on the surface. That temperature exceeds the melting point of lead. It's enough to soften and deform metals used in conventional spacecraft construction. Then there's the atmosphere itself, 96.5% carbon dioxide, essentially no oxygen, saturated with sulfuric acid droplets falling from the cloud layers above. Any one of these conditions alone would be a serious engineering challenge. Together, they create something that we have never found a way to survive for any meaningful length of time. The Venera 13 record tells this story better than any description can. Venera 13 was the most robust lander the Soviet program ever built. It was engineered specifically to handle Venus's conditions. It had been tested, reinforced, designed with every lesson the Soviets had learned from the probes that came before it. And it lasted 127 minutes on the surface before going silent. That's just over 2 hours. Now think about what rovers do on Mars. Opportunity was designed for a 90-day mission. It kept going for 15 years. The difference between those two numbers is not a difference in engineering quality. It's a difference in what the environment demands. Mars is a place where our engineering can keep up. Venus is a place where our engineering loses quickly every single time. There's no other world where we've sent hardware and had it defeated that thoroughly, that fast. Not Mercury, not Io, not Europa, not the depths of Jupiter's atmosphere, where the Galileo probe actually outlasted most Venus landers before pressure finished it off. Venus is the record holder. It's the environment that most completely overwhelms what we can build. The pressure, the heat, the corrosive chemistry, they don't take turns. They all arrive at once, immediately, the moment a spacecraft reaches the surface and the clock starts counting down from that instant. Nothing we've ever built has lasted more than 127 minutes on Venus's surface, and it wasn't for lack of trying. It's that Venus is operating at a level of hostility that simply defeats current engineering. There's something almost cruel about how beautiful Venus looks from Earth. Step outside on a clear night, find the western horizon just after sunset. It's there. A hard, brilliant point of light that doesn't flicker the way stars do. It's steady. It's bright. It's the kind of bright that makes you stop and stare for a moment before you realize what you're looking at. Nothing else in the night sky looks quite like it, except the moon. That brightness has a specific cause. Venus is wrapped in those thick sulfuric acid clouds we've spent so much time talking about. Those clouds are extraordinarily reflective. Venus reflects about 70% of the sunlight that hits it. That reflectivity is called albedo, and no other planet in the solar system comes close to matching it. Earth reflects about 30%. Mars reflects even less. Venus bounces most of its incoming sunlight straight back out into space. From where we stand, that reflected light is intense. On the darkest nights, Venus is bright enough to cast faint shadows on the ground. It has been photographed producing visible light on snow-covered landscapes. The planet itself is an inferno. Yet the light it sends us is clean and cold and almost serene. People have mistaken it for aircraft. They've reported it to air traffic control. There are documented cases of military pilots scrambling to intercept it. UFO hotlines have received calls about Venus more times than anyone has bothered to count. It sits near the horizon in the early evening or early morning. It doesn't move the way stars move. To the untrained eye, it looks exactly like something artificial, something large and close and deliberate. It's been generating confusion and wonder for as long as people have looked up. Ancient civilizations didn't have telescopes, but they tracked Venus with extraordinary precision. The Maya built an entire calendar system around it. They calculated the synodic period of Venus, the time between successive appearances of Venus in the same part of the sky, to be 584 days. The actual value is 583.9 days. That's not an approximation. That's a measurement so accurate it stands as one of the most impressive astronomical achievements of the ancient world, made without any instruments we would recognize today. The Maya tracked Venus because they believed its appearances governed the right timing for warfare, for agriculture, for almost everything that mattered. It wasn't just a beautiful light to them. It was a clock. Many ancient cultures looked at Venus and thought they were seeing two different objects. In the morning, before sunrise, it rises in the east ahead of the sun. In the evening, after sunset, it appears in the west. It can't be seen at both times on the same day. To observers who didn't have a complete model of the solar system, the obvious conclusion was that these were two separate things. Two separate stars, or lights, or gods. The Greeks called the morning apparition Phosphorus and the evening apparition Hesperus. These were treated in the early Greek tradition as distinct. The Pythagoreans are often credited with recognizing that they were the same object, though the precise history is debated. By the classical period, Greek astronomers had worked it out. Phosphorus and Hesperus were the same planet, appearing on different sides of the sun as it moved through its orbit. The Babylonians got there earlier. The Venus tablet of Amisaduqa, dating to somewhere around the 17th century BCE, records systematic observations of Venus's appearances as both the morning and evening star and treats them as the same object. The Babylonians were meticulous observers. They tracked Venus's appearances over decades, recorded the intervals between them, built predictive models that were sophisticated enough to anticipate future apparitions with reasonable accuracy. They were doing this more than 3,000 years ago. What none of them could know, what no one would know until the space age, was what was actually underneath those clouds. From Earth, you can't see the surface of Venus. The clouds are too thick, too complete. Every observation of Venus from the ground is an observation of the cloud tops, roughly 70 kilometers above the surface. All that precision tracking, all those centuries of careful observation, they were watching the outer layer of a sulfuric acid shroud surrounding a world hot enough to melt lead. The beauty was real. The horror beneath it was completely hidden. Then there are the transits. A transit of Venus is one of the rarest predictable astronomical events visible from Earth. It happens when Venus passes directly between Earth and the Sun, appearing as a small dark disk moving across the Sun's face. The geometry that makes this possible is rare. Transits come in pairs separated by 8 years. Then those pairs are separated by more than a century. The pattern runs on gaps of 121.5 years, then 8 years, then 105.5 years, then 8 years, repeating. In all of recorded human history, only 7 transits of Venus have been observed. The transits of 1761 and 1769 were major scientific events. Astronomers realized that by observing the transit from widely separated locations on Earth, measuring the slight differences in the timing and path of Venus across the Sun, an effect called parallax, they could calculate the distance from Earth to the Sun with unprecedented precision. Knowing that distance was the key to knowing the scale of the entire solar system. The international effort to observe the 1769 transit was one of the first truly global scientific collaborations. Expeditions were sent to Siberia, to Hudson Bay, to Norway, to the Pacific Ocean. Captain James Cook's first voyage was partly organized around observing that 1769 transit from Tahiti. He did observe it. Then he opened sealed orders from the British Admiralty and sailed south to search for the hypothetical southern continent. The transit of Venus launched one of the most famous voyages of exploration in history. The last transit of Venus was June 5th and 6th, 2012. Millions of people watched it through solar filters and online streams. The next one won't happen until December 10th and 11th, 2011-17. Everyone alive today who watched the 2012 transit watched the last one they will ever see. There's an irony in all of this that's hard to get past. Venus is the object in the sky most frequently mistaken for something extraordinary. It has inspired mythology, religious symbolism, calendar systems, global scientific expeditions, and centuries of careful observation. Ancient cultures built their understanding of time partly around watching it move. Modern astronomers have used it to measure the solar system. It is, by every objective measure, the most visually striking planet in the sky, and it is, by every objective measure, the most hostile world in the solar system. The same clouds that make it so luminous are made of sulfuric acid. The surface beneath them is hot enough to melt lead, pressurized enough to crush a submarine, toxic enough to kill instantly by any of several independent mechanisms. Every spacecraft that has ever reached its surface has been destroyed within hours. The best one lasted 127 minutes. The most brilliant, beautiful light in the night sky. And underneath that brightness, underneath those gleaming clouds, is a place more hostile than anywhere else we know.